asked to get this.
Recording in progress.
Oh.
Whatever you say, it's for fussing.
All right, now we're on record. So anyway, I was asked to get this puppy started. So do we have our slides or?
Yeah.
All right, thank you. Oh, all right, here we go. Anyway, as you guys may remember, I'm Amber Parrow KD5YQU. This is my husband, Nathan Parrow KC5YTH. We're the owners of Oklahoma Robotics. And what Oklahoma Robotics does is we do a lot of work with automation for manufacturing and industrial applications, as well as prototype design. Today, we also have Beau Schwabe. He does a lot of our circuit board design and also programming. He's also got all the cool stuff, so you definitely want to talk to him. And then we also have John Mortenson, who's also my dad. He's an electrical engineer, and he has a long career history of automation systems and automation work in the oil field. So today we want to come and share with you a little bit about some of the projects we've done, but not only our projects, but also the process we go through. We started out about 15 years ago. We've been debating the timeline on this as a hobby and as a club. About 10 years ago, it turned into a business when we started getting paid projects. And 3, maybe 4 years ago, my husband quit his day job and took this full time. You'll find us in Southeast Oklahoma City. Just give us a shout. We'd love to have you come by and stop at the shop. And the thing you need to know, it's basically a playground. So be sure to come by and visit us. I did want to go through our process, and it's got really cool takeaways, not only for our commercial industrial side of things, but also if you guys are also working on projects, just some basic engineering process. First, we'll start off with like an evaluation, then a brainstorm, research, design, and the deployment. So to get this started, we're going to talk about evaluation first, and I'm turning this over to Nathan.
Hi guys, this is Nathan Parrow KC5YTH, and I'm the owner of Oklahoma Robotics along with Amber. And we want to tell you about the process that we go through when we meet with a new client. So the first thing that we do is we want that client to take us and walk us through their facility. So we go into their facility and we see what they do, what their current processes are. In a manufacturing environment, there's a lot of activities taking place, and there's a lot of different things that go into making a product. And so normally in any manufacturing environment, there's always something that is creating a pain in the process, something difficult, something that's slowing down the process, something that's making it difficult for them to get as much product out the door as they would like. There's also factors like human injuries and different things that people are experiencing difficulty doing something. One of our clients makes pipe, and they have these rubber gaskets that have to be installed inside a groove in the pipe. And on the larger pipes up in the 6 and 8 inch range, that's no big deal for a person to do that, stick their hand in there and put that in the groove. But they also make pipes all the way down into the 2 inch range. And they've had a lot of repetitive motion injuries with people trying to get inside there and put the gasket inside that groove, because it's about 3 inches deep inside the bell of the pipe. So they've contacted us and said, hey, come look at our process and take a look at this and see what we can do to automate this. Well, inserting a flexible round gasket inside a seat, inside a groove, inside a small pipe is no easy task. Okay, just holding on to that gasket has proved to be very challenging. So our engineering team has spent a lot of time developing a gripper that can grab onto that seal, hold it tightly, stick it down the bore of the pipe, locate the groove, and then open it up inside there. And then one of the things we wanted to show you today, Beau has a custom sensor that he designed to be able to check that the seating of that gasket in the system. Why don't you go ahead and show him that, Beau? That's
Yeah, can we get the video on that?
Sure.
Show that.
So this board that he's made here, I'm gonna pass the mic down to him.
Okay, so let's get that up and running here. So let me reset this. Okay, so if you see the screen, basically it's representing this has 24 sensors all the way around, and it's sensing in real time. I don't know if you can see that. The red is a little bit difficult to see, but the red is indicating error as far as outside of roundness. And so what we would actually do is we would insert this down into the pipe, and if the ring is seated properly, then you would see a bump equally all the way around. You would see it go red and then back out to green when it hits that ring that's inserted. If the ring somehow is not inserted properly, what happens then is that you'll see kind of an obtuse, or a shape that's not exactly round. So we'll know that if the ring isn't seated properly, we can readdress it as far as trying to reseat it. If you put your hand up there, Amber, and then I'll normalize it while your hand is there, it senses in both directions. So when I normalize it, it basically is saying, okay, that's normal. Now, if you take your hand away, now you can see that it goes inward. Now, if I normalize it again and say, okay, that's normal. Now, if I put something towards it, it bulges out. So if you have a ring, basically you insert it in the pipe, you normalize it, and now as it's going down the pipe, if it sees that O-ring and it's where it's supposed to be, it'll go outward because it's sensing that ring. It'll go outward. They'll all go outward at once and then go back to green as you're progressing through. If it's lopsided like it is with my hand right there, you'll know that the ring is not seated properly. Does that make sense? So that's essentially what this sensor does.
What is it used for technology for sensing?
Oh, it's just infrared actually, but it's yeah, it's just an infrared. It sends out an infrared and then it looks for reflection back. But like I said, there's a normalization feature that says, okay, whatever they're sensing right now, it's normal. And then it's what's the word? It's dynamic in the sense that it's ratiometric as far as the sensing ability. So once you define normal, it's going down the pipe and it says, okay, these sidewalls, are all consistent until we reach something that's an anomaly. It can be a hole in the pipe, it can be a groove in the pipe, it can be a ring in the pipe. Any obstruction in the pipe we can identify by just going down, inserting this down into the pipe.
Thank you, Beau. Got a little off topic there, but I wanted to show you guys that sensor. That's something that we've been working on for a while, and it's kind of a cool demo of one of our custom boards. Anyway, so we sat down with this customer and we identified that this problem that they were having inserting these gaskets into these pipes was a big problem for them. They were trying to hire low-cost employees, $12 to $13 an hour folks, and they couldn't retain them. Everybody was quitting after a couple of weeks because their hand would get sore and they would just be fighting with this thing so much. So they couldn't keep an employee in this position. And so it seemed like a prime candidate for automation. So then the next thing that we did, since we had identified, the issue that they wanted to address, we moved on to brainstorming different ways to solve that problem for them. And we did a lot of research going out in the existing market, because the one thing that we never want to do is design a custom solution if there's already an off-the-shelf one. It's always more expensive to build a custom solution than it is to just purchase an off-the-shelf machine that already does what you need, right? So we put a good bit of effort into trying to see what was out there in the market to insert O-rings or gaskets inside a tube. And there is almost nothing. It's amazing. You would think that they would have that in the automation industry. There's two companies that had something. We contacted the first one and they said, we gave up on that long time ago. We never could get it to work right. Okay, so the other one had a working solution, but it could only go down to about a 2-inch depth before they started having trouble with it. Nobody had anything that would go in 3 and 4. On the larger pipes, we have 4 and 5-inch depths, insertion depths on those. So nobody had a solution. So then it was time to design a completely custom solution for this thing. And that, took us to the next phase of our process, where we sit down with our engineering team and we look through the problem and we just try to come up with ways to solve this. So we have several mechanical engineers on our staff, and we spent a few days, actually probably a few weeks. We tried about 6 different methods to put this thing down the bore, and they were all failing. This is challenging, let me tell you. So we finally settled on a mechanical clamping system and some custom shaped jaws that could hold on to that ring, because the ring is bigger than the diameter of the pipe. It has to seat out into a groove. So you can't just hold it and stick it down the bore. It has to be shrunk. It has to be compressed down. So we've come up with a system where you have 2 jaws that are hemispherical or semicircular, half of a circle, and a pair of pins that compresses the ring into slots in those jaws, and then they clamp down on those tails. Then the thing puts it down the bore and opens up inside there. And I'm sorry, I really wish I could share all this with you, but the details of the design are proprietary to this customer, and I'm not allowed to actually show any of it. Okay, that's another thing that's important for us, is protecting that customer's intellectual property. So I can talk a little bit about how this works, but I can't show pictures or videos of this thing. Anyway, you take that compressed O-ring, stick it down the bore, and then open it up inside there. Well, that leaves 2 little bumps, if you can envision this, where the jaws compressed it into the upper and lower parts of the groove, but not the sides. So now we have to address that. So we recompress the tool, rotate it 90 degrees, and then open it again to seat those other bumps. And then we come back in with this sensor and check the placement. So what am I supposed to be talking about here? Oh, sorry. Got off on a tangent again on the tech stuff. That's the part I like.
You gotta do that. How long does it take to put it in and do all of it?
Well, it's a fairly quick process. We're using some of the smart servo motors that are out there to be able to calibrate and maintain position throughout the whole thing. So it should be, again, we're still in the process of building this version of the thing. So the placement should take place in about 3 to 4 seconds. Yeah, it should be much faster than a human can do it.
This pipe is good. The pipe is being manufactured, coming off an extruder, and then they bail the end. They bail the end, and then they cut these grooves in there. So it's a continuous process. So we have to take and receive the pipe, do all the different various things we're doing to it, including putting the ring inside, and then have the pipe exit our part of the machine, and not slow this thing down anyway. So we have a certain amount of time for every station to perform our operation on it. So.
Right, it's coming off an extruder that runs continuously, and if it has to be shut down for any reason, it takes hours to recover and start back up.
Well, that sort of leads into our next point of design. Wait,
Okay,
well,
design was what, we just went through that. Anyway, so once we've come up with an idea, then it's time for the engineering team to start designing all the parts. And it's not enough to just come up with the concept. We have to actually turn this into working, moving mechanical parts. And there's a lot of things to take into consideration when you're designing mechanical parts. You guys, some of you may do some dabbling with some 3D printing or machining, anything. Anybody do machining? No? 3D printing? A little bit? Okay. So there's a lot of design considerations for these different processes. If you're turning a part on a lathe versus putting it in a milling machine or 3D printing it. You can draw geometries in CAD program that can't actually be made. Yeah, you can. It's just you have to put a lot of thought into where the features can go, and then into how much cost in material and production time has to go into that, right? Every feature that has to be machined on a part costs money. So if you're making one or two of a part, it's not a big deal, but if you're going to make hundreds of them, it gets really expensive really quick. So when from a design standpoint, you just have to put a lot of thought and effort into making the parts simple and finding off-the-shelf parts where you can to use in a product, right? If you design every part in that as a custom part, it takes a lot more effort to build the thing than if you just make, use a lot of off-the-shelf parts where you can. So once all the parts are made, you put it together and build it and then start testing it. And a lot of that goes over to Beau for programming, right? Because now we've made the part and it theoretically should do what it's supposed to do, but somebody's still got to program all the motion sequences on it.
Right.
Right. So you want to elaborate on that a little bit?
Well,
What languages you use and
typically the approach that I use, I consider myself kind of old school. I prefer my programming language. I prefer assembly language, but there's other programs that I use. But the process, what I initially do is I try to figure out, what needs to be done. And again, old school, I like to do a flow chart. I think flow charts are worth their weight in gold, because as far as keeping things straight, you can do a one-to-one correspondence between the flow chart and the program itself. If you have to go back to the program a week, a month, a year later, it's a lot easier to get your head back into it and make a change if you need to, or you just switch gears basically. I mean, we've got so many different programs going, in my line of work throughout a daily basis, that I've got to be able to switch from one project to the next and be able to get my head into every single one of them within a timely fashion. And so flow charting is really, for complex designs, is really the only way to go as far as I'm concerned. And it just makes the structure of the program much easier to maintain. But no, as far as programming and designing circuit boards, that's kind of my wheelhouse as far as what I do. I've had a hobby in electronics since I was 8. Taught myself assembly language when I was 12, and just kind of self-taught all along the way. So it kind of comes natural as far as that goes, as far as the process. But you learn a few things along the way. I mean, when I first started out programming, my structure was completely different. And you have, through experience, you learn different techniques and different ways of doing it. So, and streamline it along the way.
another piece I forgot to mention in there is John's part of it. And then, some of these machines that we build are quite large, and we have to have power distribution and data cabling and electrical panels laid out and all that. So tell them a little bit about what you do on that.
I think Beau and we tend to work on the tail end of these projects. So the machine's been defined, it's been designed mechanically. Well, it just sits there if you don't apply power to it of some kind, whether mechanical power, electrical power, whatever. And we always have to have feedback from sensors of various types. And so once as a machine is being designed, then I'll take that design and apply all the sensors. Well, then I have to wire all this, bring all the sensors into a control cabinet. We also have to have power. Sometimes we're dealing with 480 volt, 3-phase power, and OSHA requires us to keep all that kind of stuff. Anything that's over 50 volts has to be kept in a separate enclosure away from non-qualified personnel. And so I have to separate those two out and then have interconnects between the two. And then how's the cabling going to operate with this machine? This machine's moving, so we have to use cable chains that you probably have seen these things before, but it's just a chain. It's a flexible wire duct. So as the machine's moving, the wires are moving with it, and so we have to take all that into account. Well, then all the different sizes of wires. You got instrumentation cables that are twisted pair, or they may be shielded. They have power that has a certain size. So we have to figure out, okay, here's all the cables that are going from point A to point B. What's the cross-sectional area of those cables? And then how much space is it going to require in this cable chain? And how long does it have to be? How much does it have to move? There's a lot of design that goes into all that stuff. And then I'll work with that. Well, then my cable chain becomes in the way of some mechanical things. So I have to coordinate all that with the mechanical motion of these machines. Then we have to tell it how to control this thing. And so, if you can't control something you don't understand, so I'm the controls type guy, but I tend to want to have to understand the mechanical side of it too. So I accuse Nathan often of trying to turn me into a mechanical engineer. So anyway, so I get very involved in that, even in the early meetings with the customers and trying to understand the concepts, because, it might sound like a good plan, but if I can't control it, then it's probably not going to work. Then I'll lay out, once I get everything identified, I'll lay out all the terminals, lay out the cabinets and using wiring ducts and just all these years of experience of laying these things out, because somebody's gonna have to wire it up. Well, again, like Nathan said, you can design things you can't build. So I don't want to design a control cabinet that somebody can't build and somebody can't maintain. And all through that process, I'm trying to be very diligent in documenting it all. I use a lot of 2D CAD to lay out the schematics, wiring diagrams, process flow diagrams, all those type of things, so that at the end of the project, I can just print them out and hand them to the customer, and there's our document package for how this thing is wired up. I think probably all of you guys have been frustrated over the years of insufficient documentation, or you get a document and you look at what the product is, like, this can't be the same thing. So they haven't updated it. So that's part of what I do. I've been both the creator and the victim of that type of insufficient design of this thing. Yeah. And getting some of these sensors and things, you wonder who in the world is at the manufacturer of this stuff that's designing this. So they'll tell you all about how wonderful this thing, then they fail to tell you what the voltage range is for the sensor. Like, well, how am I going to hook it up? So, sometimes we have to experiment. We have to put it on the bench and try it and see if it'll work, and see if I let the smoke out, it's going to not work. So I don't want that wire to become the fuse, that type of thing. So,
Sometimes there's a language barrier too on the instructions or the data sheet. It's not.
Oh yeah, there's a column of Chinese and there's what they interpret as the English for that. And you look at it and we have to pass it around like, what do you understand that to mean? So, it's a challenge at times. So anyway, that's the part I do. And then a lot of times I'll build the first issue of something that maybe we're going to build several of them and get it all laid out and tweak on the design. Then we hand it over to the technicians that will actually start producing, for having build more than one of them. The other challenge is a lot of the things that we build or we design, it's never been built before. It's a one of a kind. It's maybe the only one ever been rebuilt. I don't know, maybe 6 months ago, we rebuilt an old CNC router table for a customer. It's a really large router table. It's like, a 4x8 bed on it. 8 horsepower spindles on this thing. It had dual spindles. And it was a really, really old control system. And we just gutted the cabinet, took them all off. And so basically designed the electrical and the controls from scratch using a CNC controller from Australia is what we use. So we had to interpret all that and try to integrate the design into something that could be used. It actually worked.
Well, thank you, John. Okay, once the machine is built and everything's tested and working, then we have the fun part of taking it to the customer site and installing it into their production line. In a situation like our pipe making customer, where they're running a continuous extrusion process, that means we have to shut down their line. We're going to impact their operations. And so we try to make sure that everything goes together as smoothly and cleanly as possible. And we still have to, you know, wire it into their existing machinery and level it to their floor and do all kinds of handoff testing between our machine and their machine. And it just, there's so much that goes into that, you know. It's just, you think about just getting a new piece of equipment and you just bring it home and you plug it in and you use it. But even in your ham shack, I mean, you guys know what happens if you get a new antenna tuner or something like that. You have to rewire everything, right? I mean, it's not just a simple plug it in and go. And it's 10 times worse when we're talking about a machine that's 20 or 30 feet long and 10 feet wide and ties into upstream and downstream other machinery that has to hand off. So we have to go through a lot of planning on that installation process, coordinate with the customer, make sure that we can shut down their line and, you know, be ready to handle any issues that come up if things don't go as smoothly as we hope, right? I mean, when have you ever installed something that worked perfectly the first time? So yeah, so there's always that. There's a lot of on-site troubleshooting and testing and last minute adjustments that have to be made. And then of course we have to sit there and support the thing after the fact to make sure that it's running smoothly, there's nothing breaking down, and make sure that we train their staff on how to operate that machine, how to work safely around it. And then once we turn it over fully to them, we still have to provide support after the fact. So just designing and building a machine, it's got so much that goes with it from the discovery phase and just figuring out how to do something all the way through the support after the fact. It's a lot that goes into that. Anyway, in conclusion, I guess we would like to invite any of you guys out that ever want to come out and see kind of some of what we do. We've got an in-house machine shop. We've got an in-house welding and fabrication section of the building. We've got mechanical engineers and electrical engineers and lots of stuff that we do. I encourage our employees to do personal projects after hours and just tinker and learn. And I'm trying to get these two guys to step up and become ham operators. So, I still don't understand. Beau's been dabbling with electronics and tinkering his entire life and never become a ham operator. That one just boggles my mind.
Test every month in the very room you're sitting in.
It's actually kind of funny because when I was younger, you know, these personal stories. When I was younger, I was one of those Atari guys. I had an Atari computer and I listened to shortwave radio all the time. And so through after realizing that I could program the Atari, just the game system, and I could use the output ports as input ports as well. I had something that I tuned into the radio that would actually decode Morse code and print it in text where I could read it. And I had it go in reverse the opposite direction. To where if I type something in, it would actually generate the Morse code. Mind you, I was probably 14 years old or less. So, fiddling with that and doing that sort of stuff back then, it is a wonder why I don't have a ham license. And I, like I said, I've broadcast accidentally several times. So probably.
They do the testing right here.
Right.
Said, when is it? When is the testing?
First Thursday of every month.
Right.
First Thursday of every month. Okay.
All right. Well.
Both
I've got a
cool
book I
kids
can
have ham license.
Yeah.
All right. I would like to open the floor to questions, I guess, at this point. Mark?
Okay, Nathan, I'll throw it at you. I've got a question. If you would, for us out here in the amateur radio world, tell us what you could do specifically for amateur radio, since you are ham, and what you could build based on what we normally do in amateur radio world.
Well, let's go through the process on that right now. What do you guys need that doesn't exist in the marketplace? Yes, sir.
I'd like to have a robot that could climb a radio tower and install an antenna.
Okay, a robot that can climb a radio tower and install an antenna.
Yes. What you need?
What else do we need?
APRS.
Yes, sir.
I'm curious that when you design a system for your project,
Uh-huh.
Are you manufacturing your own circuit boards? Are you buying off the shelf components from SMA or through Home Technology or IC circuitry, IC chip circuitry? Do you have local resources for those things?
Well, we do design a lot of circuit boards. We don't manufacture the boards in-house. In fact, to my knowledge, there's only 2 or 3 companies in the US that have the capability of actually making the board part of the circuit board here in this country. Pretty much all of that takes place in China. We do send our designs over there for them to make the boards. If we're just doing a test run, then we don't have them populate the boards. We just have them send us the raw boards and we populate them by hand. Any kind of a production volume, 20 pieces and up, probably we have them populate them as well. It's amazingly affordable and quick. And we do have to tell them where to source the components from. And to that end, you upload a bill of materials file. Beau could tell you more about that, but you upload a bill of materials file and specify the manufacturers of the components that you want to use. Here when we populate them by hand here in the US, we mostly get parts from DigiKey and Mouser and things like that. I'm aware that there are a few local companies that delve into some of this stuff, but I'm not very familiar with them. You have some resources you would like to suggest? No, there's very little local. In fact, it's been surprising, and kind of like Mark found Oklahoma Robotics. I think we're one of only a very few number of robotics companies here that actually design and create things from scratch. Most companies that call themselves robotics companies are what we would call a product integrator. They'll take an off-the-shelf robotic arm from Fanuc or one of the other big manufacturers and integrate that into someone's production process, but they don't design and build the thing themselves. So,
Do you do a lot of 3D printing of the parts and accessories you need to make your kits work?
we 3D print stuff almost every day. We have multiple 3D printers that are running almost continuously because all the parts that we design, we want to print, test fit everything with 3D printed parts before we actually go to the cost and part of machining them. Machining is just so much more expensive, even with an in-house machining operation, than 3D printing. It's amazingly easy to just hit a button and you run through a slicer and hit a button and wait a few hours and the part comes out almost ready to use with very little final cleanup on it. It's just an amazing process. But yes, we do a lot of 3D printing.
Question from the peanut gallery.
Go ahead, Lee.
Yes, I build magnetic loop antennas, and part of the magnetic loop antenna is using a variable air capacitor or a vacuum capacitor. And the larger ones, are producing a lot more voltage or a lot more wattage. And so I'm looking at using a stepper motor to do finite control. And the biggest thing I'm looking for is, affordable in that you can use also an IR or some type of transmitter so you can separate yourself from the antenna to adjust it.
Okay, so does your process require any kind of a feedback loop to tune the capacitor, or is it something you just want to be able to turn a dial down at your ground station and it adjusts it somewhere else?
Yeah, you have to tune the station for the highest reception capability, highest S units that you can get.
Okay, so if it's a man in the middle kind of control loop, that's actually very easy to do. We've got some boards that we've designed that would allow, a potentiometer input to control a stepper motor's position. And stepper motors are very low cost. So what you would need would be the control board with a little bit of custom programming on it, and then some kind of a stepper motor driver and a stepper motor.
And you can make that wireless too, to separate yourself.
Absolutely, yeah. We've got a wireless link module that Beau's been working with. That's on 2.4 gigahertz that can transmit data wirelessly very easily, very, very low cost,
As long as that's
and
not gonna interfere with what you're actually using the antenna for.
fully encrypted as well. Yeah. How much?
Okay,
Yeah.
and also, have you heard of a company called OSH Park?
Osh Park. Yeah, absolutely.
They do boards.
Osh Park does boards.
Yes.
Yes, they do. They also have a service called Osh Cut, I believe, is a spinoff out of their company that we use for laser cutting metal from time to time. It's one of the processes we don't have in-house.
Well, I've used them for a couple of boards that I have in the antennas. That's the reason I was wondering.
Yeah, absolutely. We've used Osh Park a couple times. I'm not sure why we've moved away from them so much. I think it's largely just due to cost. They're quite a bit more
We can get
costly.
some cheaper solutions right out of China, I think. for some
Yeah,
things that we're doing.
unfortunately, and we may need to look at bringing that back because we've been having some issues with that too. So, yeah, if you're yes,
Well, I had a question about making realities and stuff. When you design this equipment, one of a kind, who owns the rights to that? Do you own the right to it?
The customer.
Buys it, own the right?
yeah, the customer owns the rights to that because we are essentially acting as an outsourced R&D facility for that project. They're paying us for our engineering time, and they own the rights to the work.
Okay. I would imagine something like that sensor may be patentable.
It may be, and it would be up to them if they want to patent it. We're showing it to you today. Quite honestly, we probably shouldn't be, but they've not expressed any interest in keeping it a secret or patenting
The
it. But
sensor itself, basically, we derived from an existing product that's linear. We derived this sensor from an existing product that's linear. We just basically took that and wrapped it in a circle. But as far as anything, a wow factor, as far as any of the electronics, it's pretty standard. I mean, it's an infrared transmitter receiver. Like I said, we've just wrapped it around in the circle. We're sending all those the values to a microprocessor, and it's sending it in a serial stream to the computer. I wrote a Visual Basic program that interprets that data so that you can see it. I mean, that there's really nothing outstanding with this. I mean, other than how we're using it. Yeah, how we're using it.
Well, I imagine that could be adapted to a lot of things like, somebody needs to check the uniformity of the interior of the pipe or something.
Right.
Like that.
Sure.
it's the form factor that's unique to it. The core technology there is not anything we developed. And that's why we're more able to share this. Unfortunately, most of the stuff that we do, we just can't show you and can only a little bit talk about it. One of our previous projects that I thought was really cool is we designed and built a 5-axis laser system for cutting dental. You guys know what an Invisalign tray is? Well, there's another company that competes with Invisalign. They're here in Oklahoma. And they make those trays by vacuum forming a piece of thin plastic over a 3D printed model of the patient's teeth. And they have a program that they've developed where they take the teeth, they scan the jaw, scan the mouth, and they take an image of the teeth the way they are now. And then the doctor sits in there and tweaks the model to make it look the way he wants it to look when you're done. And they 3D print a whole series of jaws in between there. And then they vacuum form over all those jaws. And then they have to cut the vacuum formed plastic tray off of the 3D printed model. And so they were doing that with 5-axis machining centers, which is very slow, very costly, and very, it creates a huge amount of plastic powder, plastic dust, right? That they then have to clean up. So we designed and built 2 5-axis laser systems for them that you put the model in the tray and it sucks it inside an enclosure, and it sits there and it rotates this model in front of the laser and cuts it out and then spits it out again. So all they have to do is load it on the tray, hit the button, and it comes out all cut out for them. So, yes.
Okay, so both my daughters have expressed a lot of interest in STEM and robotics and all
Awesome.
that. So is there any resources that you know of that they could start looking at for going down that avenue?
I could answer that.
Yeah, sure.
One program that we got involved with our kids, and I'm a pretty big fan of, is the First Robotics. I actually coached an all-girls league at one point, and this would be the first Lego league from First Robotics. I'm guessing, and there's also a younger Lego league as well. So they'll use the Lego platform for the building. Lego has sensors. It has a nice little WYSIWYG interface to learn programming. So you learn all the aspects of robotics, the programming, the mechanical, the software. And there was a big field, and so there were challenges. So there was also an element of game strategy, because they designed the game to be impossible to get all the points in the amount of time that was allotted. And so you had to actually develop a strategy of, I'm going to go for the points here and here and here, because I know we can build and develop. Oh, that's got a bunch of points here. It's harder. We may try it, but let's also make sure we're getting enough other points. There was a ton of strategy with that. Also, with the first, what I loved about First Lego League in particular was there's also the presentation. So even if a child had more of the artistic bent, which I'm more of the art side of things, this actually incorporated them, because, well, as today we're here presenting, we have artwork, graphics to help explain these concepts. So this program also judged you on your presentation. You had to explain a problem solution to judges. So, and then you showed, your team at a booth as if it was like a trade show. It was just, to me, it just hit all the boxes. So a really great program. I highly recommend it.
Right. If your school doesn't have it, or are they in school or homeschooled or?
They go to small school.
Okay, if your school doesn't have it, there's a group in town called the STEAM Engine. And I believe one of their core goals is to help find ways for kids that are interested to participate if their school doesn't have a program. We've attended a couple of their events, and they seem to be really great folks. And you might reach out to them if the school doesn't have it, or you can always start your own group. There are a lot of homeschool groups that do this. They get enough people together to form a team, and you can compete at the local and regional and state levels all the way up to nationals if you can make it that far. But like Amber said, they put together a trade show booth. They put together a presentation for the judges on what their robot does and why you chose to go that direction with it. And then they have to actually build the robot out of Lego parts that are in the kit and program it to do a series of challenges. And it's a whole new field and challenge every year. It's a really cool program. So
if you would show us your two robotics that you brought this morning, and explain a little about both of those. And
okay. Well, if Beau can get that powered up over there.
Real quick question.
Yes, sir.
What's the address of your location?
We are at 1528 Southeast 27th Street in Oklahoma City. Yes, sir. Back there behind the McDonald's. So this platform here is a technology demonstrator. This was a customer had a project that they needed a platform that could self-level on uneven terrain. The intent was to make a very large scale version of this and set it underneath a cargo helicopter, drop it in the field. I think it's even
maybe
smaller than that. I think it's 1/16 scale or so. Anyway, just to, do a proof of concept for the customer to use with some potential investors that they had, we built this small scale model. And again, the intent, it's kind of interesting to show, Beau, if you'll actually stick something under one of the legs, you'll see how it adjusts to uneven terrain. Well, it just takes a second. Stick it up on the laptop or something if you need to. Just enough to cause it to be off kilter and uneven.
Here's a good use of correct radio amateur book.
It's only standing on 3 legs, but yeah, there you go. It's too well balanced to do what it needs to do. But basically it just tries to return the platform to level all the time. There's an IMU sensor on the bottom that reads the current level state, and then the microcontroller sits there and filters the results. And the IMUs are very unstable and jittery, and so there's a lot of filtering that has to go into the code on the micro to stabilize that. And so that's basically just a small concept.
So that keeps your beer level? Is that
Concept model. Yeah, it'll keep your beer level.
what kind of concept would that? What kind of concept would that prove? To me, it looks like a offshore drilling rig trying to.
Well, I mean,
stabilize.
yeah, because I mean, this is basically designed to be dropped from a helicopter. So you'd have, chains going up to a point, and as it's dropped, it would actually land from,
It would be sat down under helicopter on an uneven terrain, and then it would self-level and allow it to deploy what it was supposed to deploy, which I can't talk about.
Without killing me.
Yeah, so
I
anyway.
was about to say,
Anyway, and then over here we have the Kettybot. Now this is not normally what we do. I brought this today because it's a really cool demo piece and people love to see robots driving around and stuff. The Kettybot is made by Robotics out of China, and this was a demo unit that they've got on loan to us. And these are designed to work in restaurants. With everything going on with COVID, the wait staff shortage and contamination issues, they came out with a whole line of robots that are designed to just bring your food out to the table. So it's essentially a non-contact system. The kitchen puts the food on the robot, tells it which table to go to. Yeah, there you go. Put the food on there. Now tell it where to go. Go ahead and touch the screen there. Okay, now pick a table. Say table 4.
Table 4? Okay.
Yeah, hit start.
Well, I didn't select it. Okay. Thank you.
And there she
Table
goes.
4,
So
whoever you are, is gonna get a donut.
table 4 is getting a donut. That's when she brings the donut over, you take it away, you hit the done button, and she goes back to the kitchen. It's just that simple. So this robot has a built-in LiDAR scanner down in the base. There you go. All right, you got him a donut. So this has a built-in LiDAR scanner, and this morning before most of y'all got here, what I did was I took it and I pushed it around the room and allowed it to create a map of all the tables and everything that was in the room. And then I assigned a variety of tables, different numbers. And now it's going to adapt. Mark's standing in the way.
It's yelling at me.
Mark's standing in the way, so it's trying to find a way around him to get back where it's supposed to go. And if it can't find a way, it'll say, I can't get through, please move. So, yeah. Anyway. Yeah, I think I misprogrammed this as table number 7, but
Did you say it's LiDAR and the same technology, self-driving cars?
very, very similar, yes. This one only creates a 2D map of the level right around the floor, people's legs, tables legs, and stuff like that. So, the self-driving cars need more 3-dimensional data. This is a very low-cost, simplistic thing. But China has us; they kick our tails on this stuff all the time, guys. What if you had to guess what something like that cost or would retail for, what would you think? So it's right around $12,000 to $13,000 to deploy one of those units. And it's just, you know, the technology that's in it, it's got dual displays, like 5 cameras, the LiDAR system, the motors, the battery, lithium battery. There's so much stuff there for, you know, their cost on it has to be less than half that to be able to actually sell it through a distributor at that price. And they're shipping these things by the tens of thousands.
They're actually using these
Oh yeah.
in restaurants?
These are in fact, a lot of Asian restaurants are completely operated by things like this.
There's also the.
It's starting to catch on here in the US. They're all over Europe. They're all over Asia. California's hitting them pretty hard. McDonald's has signed with one of the companies for to deliver some 30,000 units or something like that in the next 6 months. So it's getting crazy. It's going to that.
So do you have to tip the robot?
No tipping needed. And
we've tried to mechanically tip it.
the cat likes to chase it.
Yeah, when we first got it, we tied like a Christmas string to it, and the cat went nuts. The cat just loved it, chased it all around the building and everything.
So if I do 2, will it go to both of them?
It will. It'll go to up to 3 in a sequence there.
Well, you didn't put a donut on it. Come on.
I think we're running out of donuts.
Tell it that you acknowledged it, that you acknowledged it, come by.
I have to wait for somebody else. Good luck.
Yeah, sorry guys, I didn't program tables over here because there were cords all over the floor and I didn't want to try to get tangled up in those, but it's yeah, that's the thing. Like the front screen can be programmed with all kinds of advertising and menus and things of that nature. Yeah, I didn't have time this morning to set it up. I wanted to put the ARRL logo on there, but I didn't get it done. So and you guys' logo. So
There you go.
yeah. All right. Here's robot stickers here if you want some. That's it. It's pretty easy. And Mark, you were here this morning. How long would it take me to map the room?
Oh, not very, it didn't
Like
take very long.
5-10 minutes. I just wheeled it
Push
around.
and 5
Yeah.
minutes. Grab the sticker and hit done. Yeah, I didn't realize what he was doing. I thought he was lost and he couldn't find the front of the room. He kept driving around and he finally came back and went, oh yeah, I programmed the whole room.
Yeah.
But he found each table and
It's
kind of neat.
I think if you don't hit done, then she'll time out.
yeah, she times out. There she's
Just
timed
like
out.
a
There you
waitress.
go. All right. Any other questions?
What's next? What do you got? What do you see a year from now? What do you see a year from now?
Oh man, I'll tell you what, we're in some difficult economic times. I don't know what I see a year from now.
Yeah, but that'd be great for automation.
It can be. We've got to return some of the manufacturing, even if it's automated, to this country, guys. It's a real problem right now. We have several crew members laid off because we can't get materials in the door to build the things that we need to build. Just getting steel is taking weeks. Sheet metal, square tubing is taking weeks. It should not take weeks to get steel. We had at one point steel factories here in this country. We've got to get them reopened. I mean,
Where do you buy your steel from?
there's several distributors around town that we use trying to find the best prices. I think usually Albright or Ray Albright or one of those has some of the better deals. We're a small volume shop because we don't manufacture a product, we make one-off stuff. So we always need some square tubing or some square rod or round bar or whatever. It's always something different. Special metals, metal supermarkets, but it's, trying to get that stuff. And I'm not talking about weird stuff. I'm just talking about like 18 gauge sheet metal, just raw steel sheet metal. Sometimes 2 weeks lead time on that stuff. I just tried to get copper bar. I got it faster, fully machined and plated out of China to my spec than I could just get the raw stock here.
Yeah.
It's just really sad. So I hate to say I don't know where that's going. I would like to think that it's picking back up and we're going to get stuff going here again. But if China and Russia continue to, slow our supply chain and make things difficult for us, this could be a really tough time.
I can see that.
Yeah.
Great time to automate because of people, but you can't get the stuff to
I
do it.
can't get the stuff. Yeah, we're so far down the rabbit hole that, as we're clawing our way back to the surface, it's just, I can't do everything in house. I can't make the steel. I can't dig the iron ore out of the ground. I have to be able to buy something at some level to make the parts. I can machine the parts, but if I can't get the steel, I can't run my machine to make parts.
I had a friend that was looking for a new air conditioner this week. He was quoted 42 weeks on a Sears 16 machine.
Well, we were quoted, what was it, electrical panels? Originally, we wanted to get some electrical panels for a project, and it was 12 weeks, and then it was 24 weeks, and then it was 64 weeks. And the breakers, all this stuff that goes in it. So we're having to make our own electrical panels now.
Yeah.
We're having to buy the sheet metal, which takes 2 weeks to get, and then, punch it out and weld it up and powder coat it and do all that stuff to just make our own electrical panels because we can't buy them.
Yep.
It's terrible.
Well, I really appreciate your efforts and your time. Thank you very much. These are really neat toys and tools.
Enjoyed being here. Thank you, guys.
Let's set for a 5-minute break and come on back.
Hey, Mark, give him that cram book.
That's on the counter.
First Thursday every month.
You see him playing with it now. It's that was our level adjuster piece, but yeah. Always got to get an ad for a cram book in.